Everyone, this is Arun Sharma from MIDAS and today we'll be talking about nonlinear dynamic soil structure interaction analysis in MIDAS Civil. And this is what we'll be covering today. I'll be talking about the new development for dynamic soil structure interaction in MIDAS Civil. And for this we had two main developments. One is general spring support, where we have coupled the stiffness matrix with mass and damping matrix. It's a 6x6 coupled matrix, and I'll be covering its feature, its advantage, its benefit, and using some evidence models to convince you. Then we have the second development as inelastic hinge properties, where we have developed multilinear type of links, and in that we have covered two types of links: elastic multilinear and plastic kinematic multilinear links. And again I'll be covering its feature, advantage, and benefits. So let's start with the general spring support. So first let me discuss about its features. Basically in this feature, in this development, we have developed a coupled 6x6 spring, as you can see here. So we initially had stiffness matrix. Along with this, now we have included mass matrix and damping matrix, which you can enter in this format. And the related analysis function with this new features are eigenvalue analysis fully supported, response spectrum analysis, linear time history, and non-linear time history analysis are fully supported with this feature. And how to apply this general spring support is that along with response spectrum analysis, when damping is to be considered, we must use strain energy damping. And with linear and non-linear analysis, we have two type of analysis method: model and direct integration. And there also exists a third type, which is static, but we'll not be talking about it here. So in analysis method, if we have selected model, then we must select the damping method as damping, because then based on the modal analysis, the damping will be considered. When we choose direct integration, then the damping method should be either mass and stiffness proportional or element mass and stiffness proportional. In this, under these two types of damping, the damping matrix that you have entered will be considered. And if you choose strain energy damping, then based on the modal analysis, the damping method will be considered based on modes. So this is the feature. Now what are its advantages? So as you can see here, the main advantage of this feature will be observed when you're doing a global analysis. And here you can see when you have especially for long bridges where there are multiple pier, and under each pier there are several piles, then it becomes virtually impossible to do the analysis with all the piles modeled, with the soil strata, with nonlinear springs, and everything put into one model. The disadvantage of modeling in this scenario, in this situation, is in this manner is that the model size increases to an extent that it becomes unmanageable by several software, and the analysis time increases, and even after the analysis we get results. The result volume is so big that you cannot handle that and extract the results what you need. So to overcome this kind of limitation, what we have done is we have generated this general spring support, which can replace the entire assembly with the piles and the footing there with one spring support. And this spring support will have three matrices: mass, stiffness, and damping. and how to convert the pile foundation to the relevant matrices of mass and damping, that we will cover in the subsequent webinars. But today what we'll be talking about is we have already converted them into these three matrices and how we'll apply them and do the simulation. So the advantage is for global analysis, you can simulate complete foundation behavior considering soil structure interaction with just one general spring support under each pier. So the benefits, as you can directly relate from your experience of long span bridges or group pile footing, it is a time-saving tool. It will cut down your analysis time, it will cut down your modeling time, it will cut down the result extraction time to such an extent that you'll save valuable man hours in here. Then it's a significant boost for seismic analysis, because such kind of analysis is very critical when you are working in a seismically active zone. And you need not to make any more compromises on the accuracy of superstructure behavior under seismic events, because now you can in the past what we used to do without this feature is that we used to have either a fixed support at the base of the pier, or we used to model simulate the entire group of pile by replacing them in one group of pile and trying to approximate the behavior of springs all along the pile. But now what you can do is simulate the entire footing or the foundation behavior with one support and take into account the dynamic effects of damping and the mass effects into the same support. So you need not make any more approximations for this kind of analysis. And the best part of this feature is that geotechnical engineers directly provide you the 6x6 matrix, and then many times you face a problem that where to enter these data and in what manner you should enter this. So the data entry is made very simple. You can directly punch in the numbers as you obtained from the geotechnical engineers and do the analysis. Thus it will make your entire work process and work sharing between different departments quite efficient. Now to simulate this behavior, I'll use a very simple example where you can see it's just a single, you can call it, let's say it's a pier, and at the base of the pier we have a general spring support, and at the top we have applied mass, and we will apply a kinematic motion to this structure and then see the behavior. With the support we have applied stiffness, mass, and damping matrix, and as a result, if you I have plotted the displacement of the top of the spear against time, and you can see the damping effect coming to picture as time proceeds. So in this manner you can verify very easily whether and how the support and the springs with the different type of matrices is behaving. To exemplify this, I'll go into the program itself and open a template file that I have. So in this template file, I have predefined a material and a section. You can just right click and go to its properties to see the material properties. I have applied a zero weight density material because I am applying the entire mass at the top as a nodal mass. And if you want to see the column section, you can just see it's a 60-inch wide solid round section. So what I'll do is quickly create a node, right click, nodes, and create node. I'll create one node at the origin, click apply, and then right click, go to Elements and select Extrude, and now I'll select that particular node, extrude from node to line element of concrete material and column section, and it is 20 feet high, so I'll enter the height as 240 inches and then click apply. Then I'll use zoom fit so that you can see the entire column erected here. Now I'll click close. And now, having done this, I'll apply the mass at the top of this column. So right click, or rather I can go to model and select masses and select nodal masses. Now I'll use single select tool and select the node at the top and enter the mass value as 6250 pounds per gravity unit. I'll apply equal mass in all three directions and then click apply, and this symbol notifies that the mass has been applied at the top, and since it has been applied in the MX, MY and MZ direction, so therefore we have half of the this hexagon as red and the remaining half is black. I'll close this, and now I'll go ahead and apply the general spring support. So for this, I'll right click, go to boundaries and go to define general spring type, and here I'll enter the name as foundation, and as you can see, this is a stiffness matrix. If I check on mass matrix, then I can consider stiffness in mass matrix, and if I check on damping matrix, then I can consider stiffness, mass and damping matrix together. So for stiffness matrix, I'll enter the data along the diagonal, now here I'm considering a very simple scenario, so therefore I have limited the use of this feature just for the diagonal matrix. But for the real scenario, you can always go ahead and enter data for the other columns as well. And especially for vertical piles, you'll have the diagonal values. If they are battered piles or tapered piles, you can enter the values in the other column as well. I mean, you have to enter the volume values in the other columns. And while converting the entire group of piles and the footing into stiffness, mass and damping matrix, these values will come into picture based on the arrangement of the piles as well. So as I mentioned, if the piles are battered, then you'll have some values in the in the other columns. It will no longer be just along the diagonal values. Having done this, I'll move on to the mass matrix and enter the data for this diagonal. And if you are wondering from where did we get these values, then we'll be covering this kind of exercise and show you how to convert from different arrangements into different type of matrix in the subsequent webinar. So don't worry about it right now. We'll be covering it later on. But I'm pretty sure the geotechnical engineers must be aware of these kinds of tools, and because they provide the data in this 6x6 matrix format that you can directly make use of. Then I'll click add, and we have defined the general link with the stiffness and the mass and the damping matrix. Then I can click close here, and then right click, go to boundaries and select general spring support. And now I'll use single select and select the node at which I want to apply the support. And as you can see, we have considered the general spring type as foundation, and we have entered the stiffness matrix, the mass and the damping matrix, and then I can click apply. You can have different type of general spring types. It is just one that I'm simulating. Let's say for under different pier there are different pile arrangements and different soil strata, so you will have different type of springs generated under different pier. So you can just select what kind of spring you want to apply or support you want to apply under which column, then just select that node and then click apply, and you will get a yellow colored hexagon that will show that it has applied the stiffness matrix on X, Y, Z for displacement, and rotation are X, Y, and Z. And you can see here mass and damping are considered. Then I'll close this, and now I'll move on to define the time history or the kinematic motion using time history on the structure. So I'll go to load and go to time history analysis data, and here I'll select time history load cases. I'll click add and enter the name, let's say TH for time history, nonlinear type with direct integration, and as I mentioned, here you can enter the time as, let's say, 60 seconds. The step increment for output is 1 and time increment is 0.01. And as I had shown in the previous webinars, I think in the last month series when we covered the inelastic time history analysis, I mentioned how you have to select these time increments. So you do a preliminary analysis, you find the period of the or the natural period of the member, and then take 1/10 of it, and this increment should be less than that value, or 1/10 of the or whichever is lesser. Then considering the damping method, you can choose from model, as I showed you earlier in the presentation. It can be model, mass, stiffness proportional, strain energy proportional, or element mass or stiffness proportional. So if you choose mass and stiffness proportional or element mass or stiffness proportional, then basically the damping that you have defined along with that nonlinear boundary will be considered. And then I'll click OK here. And also I'll define the eigenvalue analysis. So I'll click on eigenvalue analysis control, and here I can enter the number of frequency as, let's say, 10, and the type of analysis is line shows, and then I'll click OK and close. Now having done this, I'll go ahead and define the time forcing function. So right click, load, time history analysis data, time forcing functions. I'll click add time forcing function, and then click on earthquake data, and here you can choose from more than 50 built-in earthquake records as seen here. I'll choose 1940 El Centro site, and then click OK. So you can see the earthquake record right here, and then I'll click OK. Then close here, then right click again. Now you will specify how this time forcing function will be applied to the structure under what kind of time history load case. So you can go to ground acceleration now and select the time history load case and select the time forcing function that will be applied, and it will be applied in which direction. Let's say X direction, and then click add. You can consider multiple time forcing functions to be applied in the same time history load case in different directions, and you can choose the angle of excitation also. So it can be along the global XYZ axis by 0 degree or 90 degree. Basically this angle is from global axis in the XY plane. Then I'll click close here, and also let me define the time history result functions so that you can see some plots. So I'll go to graph, and under displacement velocity acceleration I'll click add new graph, and I'll enter the name as column top, and then I'll select the node number as number 2. So I'll just directly go and click on that node, and the reference point for this node's displacement can be either ground, or you can consider in the program to add the ground motion as well, or you can specify this displacement to be plotted with respect to any other node you want. So the relative displacement can be plotted in this software. Then you can consider the time forcing function, or the time history load case for which you want to consider the displacement for. Then click OK and close. And now we are good to perform analysis. So I'll just hit analysis, and here in the message window you can see the iterations being performed. And it took about 6.5 seconds to complete this analysis, and now we can see the results. So let's start with the vibration mode shapes and the period and natural frequency. So first let's see the mode 1. I'll check on legend, so you can see the natural period. You can see the percentage of almost 99% in the first itself, mass participation, and then you can click on the button with 3 dots to generate the table. So here you can see mass participation is for x-axis, y-axis and z-axis, and you can also see the frequency and the period. Now let me go and show the time history graph. So I'll go to time history result, time history graph, and I can select the function that I just created, and I'll add it on the vertical axis, and on the horizontal axis I'll keep time, and I'll enter the graph title as column top displacement for the time history load case that I've defined. I'll have the decimal points on x and y axis as 1, and then I'll click on graph. And this is what the program generates. So you can see the damping effect coming into picture. So this is how you can simulate the soil structure interaction and model the entire footing or the foundation with pile and the pile cap, and replace it with just one general soil spring support, and consider the 6x6 coupled matrix for mass and damping along with stiffness. Now let me continue with the presentation here to cover the second development of MIDAS Civil for soil structure interaction. The second development, as you can see, is the inelastic hinge properties, and for this we have multilinear links for elastic and plastic kinematic behavior. And for multilinear elastic link we have just one model, and there will be no hysteresis loop provided because it is an elastic behavior. But for plastic behavior we have 3 models, and we have provided the hysteresis loop for all 3 of them, out of which kinematic is already implemented. Takeda and Pivot are currently under development and will be released soon. Then we have then how to apply these multilinear type model is that while defining the links we need to select the skeleton and none type of interaction, and then you can go ahead and select multilinear elastic or multilinear plastic kinematic type of uh, springs. And some points to be noted regarding this feature is that for multilinear curve, that will control the behavior of this type of link is determined by force displacement or deformation relationship, and this has been made very easy. If you have this sort of information in MS Excel format, you can directly copy and paste your values to generate such kind of curves. So what are the advantages of this feature? So the main advantage is to simulate the foundation behavior considering soil structure interaction with nonlinear springs. So let's say consider the scenario where you have a single column system or few column system with a few piles underneath it, and you want to do a detailed analysis of your foundation. So you can apply three-dimensional springs. You can apply in X, Y, and Z directions these nonlinear springs to model the soil structure interaction for piles, and each of these springs can be uh, modeled for different soil layers. So for the top you can have different behavior, middle and then lower layer, bottommost layer you have different behavior, and the bottom you can have high stiffness spring to model the tip or the hard rock soil strata. So in this way you can approach to a more accurate and detailed analysis for your foundation and come up with the optimal design for your foundation. So what will be the benefits of this feature? To start with, easy data entry from geotechnical data, which is in the form of spreadsheets usually. You can directly copy and paste to create such kind of springs in no time. And since we can do a non-linear time history analysis with soil structure interaction, it is again a very important tool for seismic analysis in high seismic zones. Then it leads to an accurate assessment of the substructure and hence generates optimal design forces for your piles and pile cap. And this together with this feature and the previous one which I just shared, this makes it a completely one-stop solution for super and substructure analysis. So this software can serve the needs for your superstructure analysis as it has always been doing, but with this enhanced capability of substructure interaction, you need not go for your elementary analysis to different type of softwares here and there. Rather, you can do everything in this software package itself. Now I'll simulate this behavior with the same model, but the support is now being replaced with a nonlinear spring, and this spring will have the stiffness for the time being defined, and then you can basically it's a lollipop model as we call it. We have a mass at the top and then stick at the bottom, and which is rigidly fixed or has a non-linear behavior at its footing. So instead of imagining this as a column and then footing, you can consider this as a pile spring, and you can simulate this pile spring at different intervals along the length of the column or the pile member. But just to keep the analysis simple and straightforward, I have just applied it at the base of this column or footing, or column or pile. And upon analysis, you can see the cyclic behavior of or the hysteresis loop generated based on L centrocyte excitation. So you can generate such kind of hysteresis cycles. So let me go into the program itself and open a template file. So in this model, everything else remains, everything is same. You can see the same column, same height, one element, same material properties. And here we have applied two supports. Let me display them. This is a fixed support, and this is a pin support, which not even pin support. It's basically it doesn't allows rotation about x, y, or z axis, but it allows displacement along x, y, z axis. So this type of support is applied. Basically, what we will be doing is controlling the x, y, z displacement of this node using the inelastic or nonlinear link. So let's get started with that. So what I'll do, and also you would like to see the mass. Just like the previous model, we applied mass at the top of the column. This is what we have done here itself. So now we'll go to properties and boundaries and select general link properties. Then I'll click add here, and here I'll enter the name. Enter the name as nonlinear spring. Oh, by the way, these features are expect them to arrive in Civil 2012. So now I'll enter the name as nonlinear spring here, and the properties will be something like this. It will be an element type, and property type will be spring, and under spring we'll have linear stiffness for x, y, and z, which will be 400, 400, and 400. So basically I have just applied identical properties for x, y, and z direction for the time being to keep this demo or example files very simple. Then I'll go on to inelastic hinge properties and click add here and enter the name as nonlinear properties, and here I'll select spring type, skeleton, and none, and I'll apply x, y, and z directions. Hysteresis model will be multilinear model, and I can select from multilinear elastic or multilinear plastic kinematic. So I'll select plastic kinematic here and then click on properties, and here I need to enter the data. So for this, what I'll do is I have this spring data with me in the spreadsheet format. So you can directly copy from here, come into the program and just paste it. So you can see this kind of nonlinear link is created. And another good feature about this software is it automatically computes the initial stiffness from this nonlinear behavior and enters it here. So you can go ahead and modify whatever displacement and force variables here, and then the program will automatically calculate the initial stiffness and enter it here. Many popular software are not able to do this kind of simple computation, and leave it on the user to do it. Then you can click OK to define this spring. I'll repeat this step for the other two springs as well. Paste it, click OK, and OK. So in this manner we have defined this nonlinear property. I'll click close here and click OK to generate this spring. And now what I'll do is just go ahead and assign this spring or apply this spring between this fixed support and the base of this column. So I'll go to boundaries and go to general link, and I'll select the general link property, which is the linear property, and also select the inelastic hinge property, which is the nonlinear property. And here I'll apply it as an element and then click between the nodes, and the program will generate the link right here, and then I'll click close. I've also already applied the eigenvalue analysis, as you can see here. It is similar to the one I defined previously in the previous example. And now I'll go ahead and define the time history load cases. So I'll click add. I'll enter the name as so I'll define basically 3 load cases here. Case 1 will be for Rinaldi, nonlinear direct integration. The end time, the record data I have is for 20 seconds. I'll leave the damping as mass and stiffness proportional, and other parameters I'm leaving them as default. Then I'll click apply. Then next one I'll apply for Giraldo. I'll have same variables, but the record I have is for about 38 seconds. So I'll enter 38 as the end time, and the increment step is 0.05, and I'll keep the damping method as mass and stiffness proportional, and then click apply. And the final one I'll apply for El Centro side. So I'll enter El Centro, and the record is for 54 seconds. I'll change the time increment to 0.02, and I'll have the damping method as mass and stiffness proportional, and then I'll click OK. So I've defined 3 nonlinear direct integration type of time history. Then I'll click close, then right click, go to loads, and define time forcing functions. And here I'll add time functions, and in the time functions I'll add the earthquake records that I have with me. So let's start with Rinaldi. Now I'll show you, unlike the previous example where I imported the earthquake record from the database, I can also copy and paste the earthquake record from the spreadsheets. So here I have the earthquake record with me, so I can directly copy the data. So I'll copy this and just click here and paste. And it'll take a while to generate this graph because it's a huge amount of data, and as you can see the record is generated. Now you can enter any description you want, otherwise you can just click apply. Then I'll also add the record for Giraldo, Desmond, I'll come to the next sheet. I'll go right till the bottom of this, press shift, select this, copy this, and come here and paste. And again it will take a couple of seconds to generate the graph. So the graph is being generated now, and since we had a very big record set with us, so therefore it's taking that long. And once this graph is generated, then we'll go ahead and define one more, let's say El Centro site. And once we have defined that, we'll go ahead and apply them as ground acceleration onto the structure. And just like we did in the last time, we'll also define some time history result functions that are graphs, and the graphs will be for the link element for its displacement and force, so that you can see the hysteresis loop formation there. As you can see, this was about 7,566 line table. That's the reason why the program is taking that much time. The previous one was just about 1996 lines, so it was generated in no time. And since I'm running several applications simultaneously, it is obviously eating up my RAM, so therefore it is slowing down the process to a further extent. So by the time this is generated, let me see if I can pull out another model file and continue with the modeling from there. So let me just quickly create a copy of my completed model file. And so I can pull out and bring this model file where the functions have already been defined. So this is how dense the function is that I was trying to generate, and as you can see, it is a fairly long table, and it's actually 7,756 lines. Alright, so once we have generated these three time forcing functions, the third being the El Centro side, which we just generated in, just like the previous example. Now I can go ahead, go to load and time forcing function and then ground acceleration, and here I can select the time history case as Rinaldi and apply Rinaldi along x-axis. Click add, then click close here, then I'll repeat this, go to load, then go to time forcing function, ground acceleration, and select Geraldo with Geraldo Desmond, and click add here. Add here, and the third one will be El Centro with El Centro H, and add here, close. So we have three sets of ground acceleration defined, and also we'll define the result functions, for which we'll select general link, deform and force, then click add new function, and here I'll enter the name as link displacement. Let's say for Rinaldi first, dx is the deformation for that link, Rinaldi, apply. The next one will be link force for Rinaldi, ith node force is just fx, and then click apply here, and then I'll have link displacement for Geraldo and dx, and here I'll choose Geraldo, click apply, and then link force for Geraldo and ith node force fx, click apply, and then displacement for El Centro, select El Centro, apply, and the last one is link force for El Centro and ith node fx, and then click OK. So we have defined six functions, and then we get to the solid view here and then perform the analysis. While the analysis is being performed, let me check if the previous one that we were trying to do has generated the table or not. Oh yes, and as you can see, the entire graph is generated. So it takes time if the table is very big. Otherwise, it generates in no time. But now I'll continue with that model whose analysis is being performed, and you can see the analysis being performed as shown here. So the analysis performed in less than 50 seconds here, and now we'll see the results. So the results can be seen in the same order. You can see the vibration mode shapes to start with, dx and dy direction. You can click on and oh, that's my bad. It's, yeah, you can see the 97% participation in the first and two modes only, first two modes itself. And now I'll directly move on to the plot, as I can see we are running short of time now. So I'll go to time history graph, and then I'll plot El Centro link force on the x-axis, and on the y-axis I'll choose El Centro link displacement. I'll enter the name as El Centro, number of decimals as 1, and then I'll plot the graph here. So this is the same graph that I just showed in the